joining us for the 2024 ShoreGrid Fellowship. I'm Naomi Taylor.
And I'm Michael Stoshin. A cyber attack on Ukraine's power grid has caused power outages for more than 225,000 consumers in western Ukraine. The outages lasted from 1 hour to up to 6 hours.
A regional electricity distribution company in Ukraine was the first to report the power outages to its consumers. The outages were due to a cyber attack on the company's computer systems and SCADA systems, which stands for Supervisory Control and Data Acquisition.
These are computerized systems that monitor, control, and analyze industrial devices and processes. SCADA systems are made up of hardware and software, and they allow users to collect data from devices remotely.
The attack has been attributed to a Russian hackers group called Sandworm. This is the first publicly acknowledged successful cyber attack on a power grid. These hackers intended to test a remote cyber operation directed against Ukraine's critical energy infrastructure.
The malware or malicious software disconnected electrical substations, causing the blackout. The hackers used the Black Energy 3 malware remotely to compromise information systems of 3 energy distribution companies in Ukraine and temporarily disrupt the electricity supply to consumers.
Most affected were consumers serviced by Ivano-Frankivsk Oblast, where 30 substations were switched off, leaving about 230,000 people without energy. Consumers serviced by Chernivtsi Oblast and consumers serviced by Kiev Oblast.
According to representatives of one of the companies, the attacks were conducted from computers with IP addresses allocated to the Russian.
My name is Aiden Gresco, and I am the computer engineering student working on the technical information.
Hi, my name is Katie Fitzpatrick. I'm the policy and culture student.
And my name is Ethan Crosby, and I'm also on the technical side of things. I'm a computer science student.
Our case that we chose was the Ukraine power grid attack of 2015, and that caused power outages for roughly 200,000 people in Ukraine. And it was a cyber attack from Russia that messed with a bunch of their systems. It sent phishing emails to employees for a couple different companies, and then those emails had malicious code, and it went onto their servers. And then hackers were able to use that to basically mess with the servers and cause mass power outages across the country. And it caused power outages for roughly 6 hours for these customers, and it was one of the first cyber attacks that were acknowledged and performed remotely for a power grid.
There's a couple of different ways that I think we could try to prevent it. One of them would be like not having open ports in the network, so that would be enforcing that the applications that are already on the system are more isolated from external ports. Another thing would be like having better hardware overall, because it's old Russian architecture. So ideally, like serial Ethernet converters would be upgraded, which is in the architecture of the power grid. Another thing would be like perhaps to have backup RTU units, which are like these remote terminal units, and basically just upgrading like the overall hardware of the system.
CIE principles, so that stands for Cyber Informed Engineering, which is kind of the name of the game in this project. So the way that we've approached it is we've really looked at a couple that were really crucial in this case. So we looked at engineered controls, active defense, and we looked at interdependency evaluation. The idea is that take the principles of cybersecurity and you apply them to the engineering process. And so one of the ways that we're really looking at that in this project is the way that the breakers were controlled by the RTUs and by some serial Ethernet converters that were affected by the malware in this attack. Another malware to highlight in this situation was some custom designed malware to infect the serial Ethernet converters. So what happened in this case, they injected this malicious firmware into these units in the field, and it basically rendered them completely inoperable. They had to be replaced. And so one of the things that we've talked about as a possible preventative measure would be to create some sort of centralized firmware update server that would shield the devices in the field from being upgraded from just any computer connected to the network, which is what happened in this case. I think one of the major things that was a factor in this case in particular is the fact that the Russian and Ukraine infrastructure was very similar. And a lot of the Ukraine infrastructure was built on old Russian infrastructure that had been there from the Soviet era and whatnot. So I think, yes, absolutely, we need to be doing a lot to protect our grid. But another thing that's super important is just the security of the information and, for example, schematics of the systems that are part of our critical infrastructures. Keeping that information secure will play a crucial role in preventing attacks like this.
Raw input and power outputs. We have power degradation, which is the error between those two different signals that are coming through. The amplitude, which is the height of the sine waves. And then the operator of the HMI can actually enable or disable, actually trigger the open or closing of the circuit breaker. There's also a simulation control, which has a manual disconnect. It has a delay between the two different sine waves being generated. And the noise mix is another slider that would introduce noise, such as any kind of interference that would be coming through the signals on the simulation.
You can see we're using Simulink. This is the block diagram of all the different components that are involved. This diagram here is based off of these Schweitzer controllers. We saw these on our visit to Mitsubishi. So these are what control a breaker in a substation. And you can see this diagram here is an example of a network you might see at a substation to control a breaker. And this is our implementation of that. This gray block here is, you can think of this gray block almost as akin to the generator in the power grid, with parameters that can be controlled by the simulation control dashboard. This block here monitors the power condition, and it can also detect if there's a power fault. This block here measures the amplitude of the power coming in. This block here is the master controller, so this would be the RTU. So what happens in this block is we have a couple different like latch toggles, and they can be triggered by any of the fault conditions that are on the HMI dashboard, and they're designed that you cannot reset the breaker until those conditions have been cleared to a normal state.
One risk that could arise from it would be them using the simulation to kind of learn a little bit of the insides of how the system would work, and so that could possibly create some kind of vulnerability in terms of someone understanding how it works and then maybe utilizing that to create some kind of attack. Simulation focuses on kind of the secondary aspect of the attack, which is them gaining access to the HMIs and then that going into and connecting to the RTUs. But it doesn't necessarily stop like the phishing attack, so it's kind of like the second part of the attack that mainly focuses on. I believe the simulation would help with any kind of like unauthorized access to it, in terms of if they got access to one of the HMIs, then there would still be that disconnect in terms of difference of authorities, but it wouldn't stop any kind of phishing email attack or any kind of malicious code entering into the systems. I do know that you should run it at least probably 3 times because one, you'd be messing with the lockout mechanism in terms of testing the user HMI dashboard and seeing whenever it would lock you out with opening and closing the circuit breaker. Another test you definitely want to run would be with the admin dashboard to cause that disconnect on the user admin panel, the user HMI panel. And then lastly, at least for the third one, you'd want to test out like the system instability check to see if you change any of the sine wave values that would cause an automatic disconnect of the circuit breaker. And you possibly would want to run the simulation maybe a few more times after those 3 initial ones to make sure there's no outliers.
The Ukrainian power grid was built when it was part of the Soviet Union, so the Russian attackers were as familiar with the software as operators. Also, the timing of the attack during the holiday season guaranteed only a skeleton crew of Ukrainian operators were working.
Our Team 1 SureGrid Fellowship students will focus on not only how this attack was executed, but also how to prevent future attacks by hackers on the Ukrainian power grid, as well as recommendations on how to implement policy in the events of future attacks.